Today, we're going to cover a medium LeetCode question called LRU cache. In this question, you will implement the exact data structure and support two operations. For the get operation, you will return the corresponding value of the given key if the key exists, or you will return -1. For the put operation, you will either update the value of the given key if the key exists, or you will introduce a new key value pair and possibly evict the least used key if the cache is already at capacity. On top of that, you need to make sure that both of the operations can run in O1 time. There are a few constraints you want to pay attention to, including the capacity is at 3000, the key can go up to 10 to the 4th, and the value can go up to 10 to the 5th. Now let's think about how we can implement the data structure so that both the get and put operations can run in O1 time. If you don't have any idea at this moment, that's pretty normal. What I will usually do is I will try to visualize how I want to interact with the data, and usually the answer will become more obvious by then. What I need to do is to maintain a list of key value pairs in a way that when the cache is at its capacity, I know which one I should remove. Let's say we have a list of key value pairs here. Now, if we want to add a new key value pair, it's actually pretty easy to do. I can just append that key value pair to the end of a list or any data structure. Add can be easily done with O1 time complexity. Now, the tricky thing is when I try to update or get the value of a key, we also need to do this in O1 time. For example, if I want to get the value of this key 1, I not only need to get the value itself, I also need to update a pair as if I just introduce this new key value pair into a list. I need to move this key value pair around. And we know that we cannot do this in a normal list structure because that will take up to O(n) time, where n is the length of the list. There's one data structure that can do this very efficiently, and that data structure is called linked list or double linked list. In a double linked list, I will connect each node with its neighboring nodes so that if I want to remove this specific node, I can easily update the relationships for the neighboring nodes. For example, I will update the pointers for the nodes that's around this key value pair. And this can be done in O1 time very easily. In practice, what we'll do is I will introduce another dictionary which maintains the key and the node on the linked list. When I try to update or get the value of key 1, I will point to this pointer. I will return the value or update the value and also move this node around. And it's the same thing if we want to add a new key here. I will also update a key in this dictionary and then add a new node at the end of the list. But we are not done yet. There's one more operation we need to support, which is evict. In order to evict the least used key, which is apparently the top key in this list, we need to have a pointer pointing to the toppest key value pair. I need to introduce another pointer here. And it's the same logic if we want to add a new key value pair, we need to have a tail pointer here. That's basically everything we need to implement this data structure. This is a solution using double linked list. This is a very general solution that you can reuse in many other questions. I would strongly encourage you to figure out all the details by yourselves. Next, I want to talk about a different solution I found in the LeetCode forum, which is to use the building data structure in Python. I saw a lot of people will use OrderedDict or just the standard dictionary data structure. Personally, I really don't like those solutions because it's kind of cheating. The motivation behind using this data structure is that they can help you maintain the insertion order. Remember that previously when I have key value pairs like this, instead of actually building a double linked list and move this key value pair around, if you use a dictionary solution, they will remove this key and then re-add it at the end of it. Basically, the order is maintained. But to me, this is like a shortcut and you don't actually implement the solution yourself. It's just like in an interview when interviewer asks you to implement a sorting algorithm and you just use list.sort or sorted library. It doesn't really help you much if you move on to a different LeetCode question. But the idea is pretty simple. If you're interested, you can take a look at the solution at the forum. And let's move on to the coding part. First of all, I will need to introduce a class named double linked list node, since it's a node that keeps all the key value pair information. I will first have a constructor here, which will take key value as the input. And I definitely need to have 2 pointers here. One is called pre, the other one is called next, pointing to node before and after this current node correspondingly. And at the end, I will need to just keep the key value information on this node. Cool, that's everything we need for this class. Now let's move on to the LRU cache implementation. In this constructor, we first need to have 2 pointers, one pointing to the head, one pointing to the tail, as we mentioned in the previous section. So let me call this one DLL head. This is double linked list node. Since it's a dummy head, I can just put whatever value here. We're not going to use the key value in this node anyway. The same thing, I will have a tail. This is another dummy node. And after that, I need to make sure they are correctly linked to each other. I will say DL head next equals to self.dl tail. And the same thing for the other direction. Tail.priv equals to self.dl head. What else do we need? First, we need to keep the capacity information. Let's do this assignment first. And lastly, we also need to have a mapping from the key to the node, one of the double linked list nodes. Right? So I would do node by key. This is a dictionary. And yeah, that's for a constructor. For the get function implementation, there'll be 2 cases. First case is if the key already inside the self.node by key dictionary, then we need to do something. Otherwise, we'll do something else. If the key is already here, we can definitely return the value by accessing the node using the key, and then we can return the value. Right? But apart from that, we also need to come up with a way to update the node priority, as if we just introduced this new node into this double linked list. We'll come up with the details for this part later. Otherwise, if the key exists, we'll return the value here. And then in the other case, I will just return -1 here. Let's now take a look at the put function. Basically, it's the same idea, right? We will have 2 cases. One is the node. The key has exists. In this case, I can again access the node using the key. And I can update the value very easily here. However, and also we will need to update the node priority here. Otherwise, there'll be another 2 cases. One is that if the current capacity, we already have so many keys. The current number of keys already at capacity. If that happens, we need to remove a key. Okay, so no matter this happens or not, at the end we need to add a key. The way we do it is by creating a new double linked list with key and value. And then we need to somehow append the key to the tail, right? And then also update the node the key by assigning this node to that key. Right? Now, if we take a closer look at the placeholders we need to fill in, they can be actually further broken down into 2 concepts. One is to remove a node. The other one is insert a node at the end. We can basically simplify. We can break this down into 2 parts. And remove a key is remove a node, plus remove a key. Remove a key itself is just delete self.node by key. This key, right? We need to do remove a node plus remove this key from the node by key dictionary. And then this part is the same. We basically need to insert the node at tail. Once we have this concept, we can just implement 2 helper functions. One, I will call it remove node. as it says, we'll take a node as the input and we'll remove it. And the other one is insert node. And we know that when we say insert node, it means insert node at the end, at the tail. Let's first think about the remove node part. What does it mean to remove a node? It means that the node in front of you is next should point to the node after you. It's the same thing for the node after you. Its priv needs to be the node in front of you. So it's that easy, right? These two lines can help us remove it. How about insertion? We need to insert it right before the tail node. We need to modify two parts. One is the node right in front of the tail and the tail itself. For a node in front of the tail, I can access it by doing this. This next is going to be node. And the node priv is equals to tail priv. That fixed the first part. The second relationship is between the current node and the tail. Node.next equals to self.dl tail. And self.dl tail will be the node itself. Now let's try to fill in the placeholders. In the get function, actually I can call this node here. Node equals to this guy. And then remove a node, basically just calling this remove node function. That's the node there. And it's the same thing for the insertion. We know that insertion will actually append that node to the tail. But here we can just return the node value. It's a similar logic here. I can actually copy the code, paste it here. Here we know that the node value will be assigned to the new value. Now, remove the node here will be slightly different from the previous ones because we know we want to remove a specific node, which is right after the head. This is a node we want to deal with. Again, remove the node, and then we'll delete E of this node. What else? Yeah, the last one, we need to insert this node at the end. We'll do insert node at the end. Let's review again. I think, yeah, we should have everything done correctly. Now let's try to submit the answer. Let's first do a run here. Cool, everything passes. Now submit. Cool. Seems that our solution is pretty efficient and beats around 96-97% of the users. That's basically what I have for today. And thank you for watching.